Hi! Curious about what we're learning today? The topic I'm going to cover today comes from the subject Computer Organization and Architecture. Let me introduce you to the subject first. We'll get to know what computer architecture and what computer organization is. Other chapters are found related to these two concepts. According to the information that I have collected, students in CS Major needs to know how computer provides architectural support for programming, languages, and operating system. What do we get to learn in this subject? The overview of computer organization and architecture, examining the major components of computer and their interconnections with each other, as well as the outside world. There is one more key topic which the subject stays focused on, so that is processor. We get to learn internal architecture and organization of the processor. So that should be enough for the introduction of this subject. Ready to study now? So the topic that we're going to cover today is representation of given number in single and double processing format. I'll jot down the steps for you first. See all the steps. You may have a look at it or you may pause the video. But these are going to be helpful throughout the numerical. So let's get into it. So this is our question, and what we have to do is represent the given number. That means minus 9.25 in single and double processing format. So in order to do that, the first step that we'll have to carry out is convert the given number into binary form. So let me write this to make it easier for you. So in order to do this, we'll first have to separate numbers out as the numbers before the point and the numbers after the point. So we'll have to deal with them separately. So first of all, what we need to do is find out what is 9 in binary form. So you can do this by dividing it by 2. So you'll get 2 into 4 times gets you 8. So 1 is a remainder. So 2 multiplied by 2 again gives you 4, and 0 is a remainder. 2 multiplied by 1 gives you 2, so 0 is a remainder. So what we'll have to do is write it from the bottom to up. So 1, 0, 0, 1. This is what we get. So for the 0.25, which is after the point, you'll have to multiply it by 2. Now you get 0.5. So what we'll have to take outside is this 0, the number which was right before this point. So it is 0. You'll again have to multiply this answer by 2. You'll have to repeat the process until you get 1 as the final answer. Because it is the binary number, so it has only 2 numbers. There are only 2 digits, which are 0 and 1. So until you get 1, you'll have to continue with this process. So 0.25, while we represent it in binary form, is 0, 1. So there is a difference. I'll make you clear about that. Here, in case of 9, we've divided. And in case of 0.25, we've multiplied it by 2. So when we write down the answer, we go from bottom to up in this case, whereas we come from top to bottom in this case. So alright, so 9.25 in binary form would be 1001.01. I hope you understood. So the second step that we'll have to carry out is normalization. So this is the number what we got as binary number. So we'll have to write this number first, and then what we have to do is, let's write the normalized form. Just copy this number, but avoid the point. The point should be placed right after the first digit, and once you place the point, you'll have to multiply the given number by 2, and you'll have to write the exponent over here, but we'll have to check out for the exponent. So you'll have to count the digits in between the point and the first digit. That means there are 3 digits, right? 1, 2, 3. So the exponent would be 3. So for single precision format, let's mention few things. Let's list out few things. So sign bit for this number would be 1, because here you can see I have taken a negative number which has minus in it. It is minus 9.25. So the sign bit for the negative number is 1. If it would have been a positive number, then sign bit would be 0. So that's the only difference throughout the numerical for representation in single and double precision format. So alright, let's move to exponent. An exponent can be represented by e. So the value of this e would be 3. And finally there is one thing, significant. Significant is a number which you'll get after the point. So 0, 0, 1, 0, 1 would be the significant. Alright. So there is something known as bias for single and double precision format, and they are different in both the cases. But for now, bias for single precision format is 127. So here's e, which is going to be our final exponent, and we'll have to add the bias in the exponent. So our exponent was 3, and we would add this to get 130. So we will again have to convert this 130 into binary form. So this would be something like this. I hope you can understand what I'm doing. So this is what I get. So 130 can be expressed something like this. 1, 2, 3, 4, 5 zeros in between. 1, 2, 3, 4, 5 zeros and 1 0. Alright, this is the answer. So now finally we'll have to represent it in single precision format. So for that we need to write down single sign bit, which is of 1 bit, and the exponent. And the exponent for single precision would be 8 bits, and for the significant would be of 28 bits. Alright, so the 1 bit number, the sign bit is 1. The exponent, the final exponent should be written. So it's 1, 5 zeros, and 1 0. And then for the significant, we have 0, 0, 1, 0, 1. Alright, so you can count it. 1, 2, 3, 4, 5, 6, 7, 8. It is composed of 8 bits. You can make it 28 bits by adding zeros in the front, but that's really not necessary. So we have finally represented the given number, that is minus 9.25 in single precision format. So now for double precision format, there is only one difference. So that is bias. Bias for double precision format. And that is 1023. So we'll have to calculate out the actual exponent. So we'll add 3 to this, because exponent was 3. Alright. So when we add this, we get 1026. So I won't show you converting 1026 into binary form again, but because I know that you know how to do that, how to carry out the process. So I'll write directly. So it's 1 8 zeros, 1, 2, 3, 4, 5, 6, 7, and 8, and this is 1 0. This is what we get. So after we get the exponent, we'll directly represent them in double precision format. So this is exponent here, and this is significant. Sorry, I actually made a mistake over here on the spelling. So this is 1 bit. Exponent in case of double precision is 11 bits, and the significant is 52 bits. Alright, so sign bit is the same as of single precision. Exponent, we just calculated it. 1, 1, 2, 3, 4, 5, 6, 7, 8, and there's 2 more. So significant would be the same. So this is done. This is in double precision format. So I'd explain it one more time to you. The sign bit is the same as single precisions. The exponent that we calculated, I've written it here, and the 52-bit significant is written whatever is here because it is all the same. You can add zeros and make it 52 bits. It is not really important. So this is how we represent the given number in single and double precision format. So let's move to tip of the day. Tip of the day. It's not actually like tip of the day, but yet I've got something to say to you. Allocate particular working area for yourself. Every time you feel like studying, just go to that place. Always sit down to study at the specific place. The reason why you need to do this, I'll tell you in my next video. But now, stay charismatic, energetic, be positive, be you. Have a good day.